Welcome to Flat Earth Debate Special Edition with Brian's Logic live. I'm your host Nathan Oakley, and if you are new to this channel or you've not done so already, then be sure to subscribe, hit the bell notification icon and join button to keep up to date with the Flat Earth Debate. If you'd like to support the channel, there is a super chat that runs alongside each of these shows while they are live. There's also a PayPal, Patreon and crypto link in the info box below the video. Now we are joined by, of course, Brian's Logic and a whole bunch of people in Discord for this presentation on the entropic effects of the sun. So first and foremost, hello Brian, how are you doing?
Hey Nathan, how are things? Thank you for having me.
Absolute pleasure. And also hello to everyone else in the G Plus panels, hopefully going to keep themselves relatively quiet while this presentation progresses. So hello everyone else in G Plus.
Hello, hello.
Yo, yo.
This is exciting.
Indeed it is, Neil. So I don't want to waste any time, Brian, because obviously with us doing a bit of a pre-show as well, you might be watching this on an after show, and therefore you've had the 7 minutes of preamble before this. But for those who are watching live, I want to just jump straight into it, if that's good by you, Brian.
Yeah, that's absolutely fine. Absolutely fine. There will be a lot of reading. Unfortunately, a lot of stuff I got from websites, and it was easier for me to just write it out and explain it in my own way than go through websites and trying to use, as they have other stuff added in to what they're saying. So I have a lot more reading than I have visuals, but it will become apparent why that is at the end of the presentation. So it will take a little bit of concentration, but I will give people openings to ask questions. And as I said earlier, if anyone needs to ask a question, just ask at any point. I'm totally fine with that. Okay?
Perfect. Well, I've got you presented.
Okay.
Hopefully everyone else will keep themselves relatively on mute, and the mic's all yours. Your presentation's up. Off you go.
Thank you, Nathan. Okay, this is called How the Sun Causes Our Gas Pressure Gradient. There will be 6 sections. Gas cycles will be 1, and convection will be 2. Temperature will be 3. Heat transfer is 4. Low vacuum will be 5, and 22 facts will be 6. Okay, section 1, gas cycles. All the gas cycles rely on the sun, as the sun's rays and heat are the antecedent for the gas cycles to even exist. Gas cycles would not only not exist without the sun, but would just stop production altogether. If the sun stopped shining, the whole system would just equalize. All 4 main gas cycles, the water cycle, the oxygen cycle, the nitrogen cycle, and the carbon cycle, would just cease to commence without the sun's interaction. If we take the water cycle, also known as the hydrological cycle, we see where the sun causes evaporation from the Earth's surface, turning water into water vapor. This water vapor then proceeds to condense at higher altitudes and become clouds, and in turn these clouds become rain, which falls back down to the ground. But this all starts with evaporation, and evaporation all starts with the sun. But the amount of evaporation is all dependent of the amount of gas pressure we have. If we didn't have 14.7 psi as an average at sea level, then we wouldn't have the correct amount of evaporation to sustain life here on Earth. As a slightly higher average pressure would mean that we wouldn't have enough evaporation, and a slightly lower average pressure would mean that we would have too much. And it is the sun, whatever it actually is, that not just creates the gas pressure and gas production, but also dictates the amount of pressure we have here at ground level. Whatever the sun is, it is just the correct size and has the exact correct amount of power output for the structure we live in. As if it was not perfectly matched with our system, then it would all fail miserably. The sun is the ultimate entropy generator, as it causes the whole system to be a dynamic enclosed system, as opposed to a static enclosed system. The sun is also responsible for the photodissociation of the H2O molecule as part of the water cycle, and the taking taking O2 from the sea, giving us the oxygen we breathe. Where does the hydrogen go? Now, section 2 is convection. The sun is directly responsible for the convection that happens within our waters and gases, with ocean movements also being partly caused by the sun. Convection is the description of the effect of matter being affected by temperature, where a change in temperature changes the matter's density, which causes displacement. This displacement causes movement within our waters and gases, as warm or less dense matter is exchanged with cooler, more dense matter, something caused by the sun again. So we can't have convection in our world without the sun. The sun, no convection. No convection, no heat transfer. No heat transfer, no cooling. Okay, that's the first two sections. Has anyone got any questions on that before we go further?
Thank you for introducing them to actually give their opinion at this stage as well. So great, no one interrupted. But yeah, if anyone's got anything to say, feel free to say it.
Just agreement. Nice summary, Brian.
Thank you, Adam. Just on this one here, I'll be coming back to this question later, where does the hydrogen go? Okay, that's connected to photodissociation. So that's the question I threw in there, but I'll come back to it a bit later. So if everyone's okay, we'll move on to the third section, because that's a bit of a longer section.
Yeah, great. Everyone happy? Any other comments? This is your chance, so take notes if not. And everyone happy?
What's Brian's YouTube channel called?
Brian's Logic. Brian's Logic. Plug your channel. Good point. As we were early on in the show.
Yeah, Brian's Logic is my YouTube channel. Thank you, John.
Perfect. Do you want to continue, Brian? I've got you presented again.
Yeah, I will, because that first two sections are pretty straightforward. There wouldn't be a whole lot of questions about it. The next couple of sections, we're more likely to have questions. So, section number 3, temperature. The sun is responsible for our seasons, so its position in the sky with respect to any particular location on the surface of the Earth dictates what season that location will be experiencing at that present time. So in June, it will be summer in the north and winter in the south, and in December, it will be summer in the south and winter in the north, with the months of September and March dictating either spring or fall north and south of the equator line. The equator region will get the most sun throughout the year, with the sun never being more than 23.5 degrees away from it. So taking this into account, we will see that no matter what season exists north or south of the equator region, between the Tropic of Cancer and the Tropic of Capricorn, will always get the most sunshine above all other locations. So the world's convection is always kept in balance due to the sun staying between these perceived parameters. As a basic description of how convection and air pressure differentials change throughout the world from the equator north and the equator south, we must look at what is known as convection cells, also known as Hadley, Ferrel, and polar cells. There are 3 sets of convection cells, both going north and south of the equator. Set 1 goes from the equator to 30 degrees north and from the equator to 30 degrees south. Set 2 goes from 30 to 60 degrees north and 30 to 60 degrees south. And set 3 goes from 60 degrees north to the Arctic region and from 60 degrees south to the Antarctic region. Below is a simple explanation and diagram to show how this happens, how this works. At the equator region, we have the most rapid amount of convection, with the air rising being less dense and more moist between the tropics, and especially at the equator than the rest of the world, as that is the region that gets the most sunshine. Between the tropics is where we have the highest amount of rising air, so this is also the region where the warm air rises highest, which also means that it's where the density of air is at its least. This is Hadley Cell 1. Next, we have the region between 30 degrees north and south and 60 degrees north and south, where we have the second convection cell, or Ferrel Cell 2. At these regions, there is still convection, but as the general temperature is not as hot throughout the year as between the tropics, we don't have as much warm air rising, and convection is not as rapid. So the warmer air meets colder air faster in the sky and at lower altitudes. Then finally, we have Polar Cell 3, between the regions of 60 degrees north and the Arctic Circle and 60 degrees south and the Antarctic region, where there is obviously the most amount of cold, dense air. So convection, although present, it is at a much slower, less rapid rate. So it's most likely to be noticed in the warmer summer months, but it still takes place throughout the year regardless, as even in winter, there is temperature changes throughout the day. This is the simplest model. This is on the globe model, if you can see it. I couldn't get diagrams bigger than this for some reason. You can see on the globe model, I'll show on a flat model in a moment. On the globe model, you can see that the most amount of convection is happening at the equator region here, and it trails off in, let's just say, it's the same over the surface, but it trails off in the height. That is the amount of height of warm air, or the amount of warm air that's rising. so it trails off. So there is like one cell, second cell, third cell at each side of the equator. But this is on the globe model. So I'll show you on a flat model. So the red is going to be the equator region, and this is the convection cell known as the Hadley cell at the cells at the equator regions, one in red. And I have it up higher as that does. This is detailing the warm air. There's more warm air, so the warm air rises higher because there's more of it. So it ends up reaching the colder air later than the other regions. Then you have the two orange ones at the sides, which would be detailing from 30 to 60 degrees north and south, where you still have convection, but the warm air is not rising as far as at the equator regions, or between the tropics, I should say, because it's reaching colder air faster. Then you have the Arctic and Antarctic what's what they call the polar cells, where the warm air, whatever bit of it there is, meets colder air a lot faster. So there is less movement and less convection at the polar cells than there is at the what's known, these two orange ones are the feral cells, and there's less convection at the feral cells than there is at the Hadley cells. So obviously, because the sun is over the tropics all the time and the equator all the time, or that's the region it stays within, that region obviously gets the most amount of convection. So, but another side effect of this is, if you can see these blue arrows I have, these blue lines where they're kind of up high here and they kind of trail down towards the polar and Arctic regions. This is the jet stream, the polar jet streams, what they call polar jet streams, where which starts at the equator and tropics region, where that warm air rises and it starts flowing down towards or out towards the colder. It's those jet streams and things like that. But once it
you're breaking up a little bit, Brian.
If I just on a basic flat model, this is the most basic description. So this is just the most basic diagram. I think things are a bit idealized with it, but this is what the best happening, even though it's very idealized. So air flows from the equator to the Arctic and Antarctic, and then back towards the equator region in simplified forms. So it's like just a one major cycle. To elaborate more on this and more stuff that's happening within it, more complexity to it, a bit later on. But this is just an introduction to the basic description of what's happening.
So, Brian, just so I can clarify. So you're saying that, irrespective of the model, these gradient convections demonstrate a correlation between the movement of the sun, the tropics, and the tropics kind of demonstrate it. And as we tail off outside, whether that's north or south, you get this massive drop because there's no path of the sun ever there, and that's where we get the least gradient. Yeah,
exactly. There's less convection happening the further away from the tropics you go, simply because that is the region that gets the most sun. So that's the basics of it.
Cool. Cheers, mate. Thoughts over.
Okay. That's fine. Yeah, no, that's exactly. Anytime you feel to ask a question, just ask, because I'd rather clear it up on that spot than go on forward with it. Okay. Even though there is minimal amounts of convection in the Arctic and Antarctic and Antarctica, the convection at the equator ensures that the warm air that rises there flows out to these regions, to these locations. Warm air flows from the equator region out towards these colder Arctic regions. It then flows back along the Earth in a cyclical fashion, kind of like it's being churned in simplistic terms. Convection is basically the pressure gradient, as the equator region is where the most region of warm air happens, with the largest volume of this warm air rising there. As we move away from the equator, the amount of warm air that rises is lessened the further from this region we get, to where we have minimal rising at the Arctic and Antarctica. Sorry, at the Arctic and Antarctica. So this means that the pressure gradient is first and foremost driven and dictated by the convection cell at the equator, which means that we have a kind of inverted cone of warm air rising. So if you're going to think of an inverted cone where you have the wide side of the cone on the base of the Earth, and it kind of tapering off up into a point, and that point will be idealized over the equator region. So this makes sense as the region between the tropics gets the most sunshine. So this has to be the region that is going to produce this temperature / convection pinnacle. The greater or maybe more consistent amount of warm air that rises between the tropics ensures that the altitude of the colder air that will displace this warmer air is at a higher point than other places. So this is I couldn't make this any bigger either. These diagrams, this just shows the difference between sea breezes and land breezes. This is important, and you'll see why a bit later. You have high pressure here and low pressure here. High pressure up here and low pressure here. So high pressure actually means cool, and low pressure means warm, because low is going to be where there's the least amount of density of air, because the air is rising because it's warm. So you have cold air over the water going to warmer air at sea, right? And then that warmer air does eventually rise and be cooled down, and that heads back towards warmer air. Basically, it makes an onshore breeze that is basically moves in a cyclical fashion. And the same happens the opposite way. If you have warm air over the water and a colder area over the land, you'll have a breeze that will be blowing out to sea, off land, if you know what I mean. So that all happens due to convection again, due to high and low pressures. A low pressure is going to be where you're going to have the least density of air, and high pressure is going to be you're going to have the most density of air, simply because of temperature. The low is going to be warm, high it will be cool. So this one here, this is another illustration that shows, like, this illustrates the amount of extra warm air at the equator region and how it creates a flow towards the Arctic regions, ensuring that convection is a constant everywhere. So this is just showing the north side, let's just say, and you can see how there is 3 different cells here. There's this one here, which is happening left of the equator region, and this one here is happening next to it, which would be, so this would be the equator, this would be 30 degrees north, this would be 60 degrees north, and this would be the North Pole region. So you have obviously 3 different cells where you have less and less warm air rising as closer to the cold area you get, and then you have the polar jet stream happening because of that. So this is the jet stream here. Obviously starts higher and it tapers off as far as warm air goes. It tapers off towards the colder region. Now, there's going to be a few times I'll have to go back over this, but I'm going to be adding things into it, other parts that people on our opposition side have ignored for many years. Okay, now I have a bit of reading to do here, and some of this stuff I'm going to have to read. There's going to be some globe stuff in it, but don't worry about that, as I can't take that out, and I'm not going to avoid reading it, as if I did, the opposition would have problems with would use that as a way of hand-waving away the presentation. But I use it against them. So I'll show you what I mean. So this is from UCAR, Centre for Science Education. The highs and lows of air pressure. There's a part in this you're going to enjoy. Okay, standing on the ground and looking up, you are looking through the atmosphere. It might not look like anything is there, especially if there are no clouds in the sky. But what you don't see is lots of it. We live at the bottom of the atmosphere, and the weight of all the air above us is called air pressure. Above every square inch of the Earth, surface of the Earth is 14.7 pounds of air. That means it exerts 14.7 pounds per square inch PSI of pressure at Earth's surface, high in the atmosphere. Air pressure decreases high in the atmosphere, air pressure decreases. With fewer air molecules above, there is less pressure from the weight of the air above. Pressure varies from day to day at the Earth's surface, the bottom of the atmosphere. This is in part because the Earth is not equally heated by the sun, Areas where the sun is warmed often have lower pressure because the warm air rises. These areas are called low pressure systems. Places where the air pressure is high are called high pressure systems. Okay, this works against them, you'll see in a few minutes. So a low pressure system has lower pressure at its center than the areas around it. Winds blow towards the low pressure and the air rises in the atmosphere where they meet. As the air rises, the water vapor within it condenses, forming clouds and often precipitation because of Earth's spin and the Coriolis effect. Winds of a low pressure system swirl counterclockwise north of the equator and clockwise south of the equator. This is called cyclonic flow. On weather maps, a low pressure system is labeled with red L. A high pressure system has higher pressure at its center than the areas around it. Winds blow away from high pressure, swirling in the opposite direction from a low pressure system. The winds of a high pressure system rotate clockwise north of the equator and counterclockwise south of the equator. This is called anti-cyclonic flow. Air from higher in the atmosphere sinks down to fill the space left as air is blown outward. On a weather map, you may notice a blue H denoting the location of a high pressure system. How do we know what the pressure is? How do we know how it changes over time? Today, electronic sensors in weather stations measure air pressure. These sensors are able to make continuous measurements of pressure over time. In the past, barometers were used and measured how much air pushed on a fluid, such as mercury. Historically, measurements of air pressure were described as inches of mercury. Today, meteorologists use millibars, MB, to describe air pressure. So here we go. Air pressure depends on temperature and density. When you inflate a balloon, the air molecules inside the balloon get packed more closely together than air molecules outside the balloon. This means the density of air is high inside the balloon. When the density of air is high, the air pressure is high. The pressure of the air pushes on the balloon from the inside, causing it to inflate. If you heat the balloon, the air pressure gets even higher. Air pressure depends on the temperature of the air and the density of the air molecules. Atmospheric scientists use math equations to describe. Someone saying something?
No, I don't think so.
Sorry, I thought it was feeding back. Sorry. Atmospheric scientists use math equations to describe how pressure, temperature, density, and volume are related to each other. They call these equations the ideal gas law. In these equations, temperature is measured in Kelvin. So they give ideal gas law: pressure equals temperature by density by constant, pressure by volume equals temperature by constant. So they are saying here that they're using the ideal gas law when they're dealing with the atmosphere, something that the opposition have been denying for 6 years now. They are stating here that they are using the ideal gas law, as they can't not be. This part here is very interesting. This equation helps us explain how weather works, such as what happens in the atmosphere to create warm and cold fronts and storms, such as thunderstorms. For example, if air pressure increases, the temperature must increase. If air pressure decreases, the temperature decreases. It also explains why air gets colder at higher altitudes where pressure is lower. Excuse me. As is blatantly obvious, there is absolutely no mention of a force of gravity here whatsoever, as that is not what causes the pressure gradient, or anything else for that matter. So, unequal heating effect of the sun on global winds. The two main factors affecting wind patterns are: one, the heat distribution between the Earth's equator and poles, and two, the constant rotation of the planet. The sun is Earth's primary energy source. However, energy from sunlight is not evenly distributed over the Earth's surface. The sun's rays are most directed at the equator, which means the ocean and air near the equator receives the most solar energy. The sun's rays are much less direct at higher latitudes away from the equator, such as the polar areas. A global look at moving air, atmospheric circulation. Even with disruptions like weather fronts and storms, there is a consistent pattern to how air moves around our planet's atmosphere. This pattern, called atmospheric circulation, is caused because the sun heats the Earth more at the equator than the poles. It's also affected by the spin of the Earth. In the tropics near the equator, warm air rises. When it gets about 6 to 9 miles above the Earth's surface, it starts to flow from the equator and towards the poles. Air that rose just north of the equator flows north. Air that rose just south of the equator flows south. When the air cools, it drops back to the ground, flows back towards the equator and warm again. Then now warmed air rises again, and the pattern repeats. This pattern, known as convection, happens on a global scale. It also happens on a small scale within individual storms. But because Earth is spinning, the air that moves north and south from the equator also turns with the spin of the Earth. Air going north turns to the right. Air traveling south turns to the left. The power of Earth's spin to turn flowing air is known as the Coriolis Effect. If the Earth didn't spin, there would be just one large convection cell between the equator and the North Pole, and one large convection cell between the equator and the South Pole. But because the Earth does spin, convection is divided into 3 cells north of the equator and 3 cells south of the equator. As above, these diagrams speak firstly about the unequal heating of the Earth. And as we have established, what causes the pressure gradient, with the sun being the cause of temperature, and temperature being the cause of convection, and convection being the cause of the pressure gradient, not a force of gravity that is 106 years out of date, to get a much clearer picture of Earth's airflow now. While I have kept this presentation as basic as possible, I must point out that it is a little more complicated than I have illustrated, but it doesn't matter, as the whole lot has a simple starting point, and that's the sun. For instance, as the sun changes its position in the sky with respect to the Earth's surface, then the amount of heat a region gets or does not get is dictated by this change in the sun's position. So this also means that the amount of convection, or just rate of convection, varies, but convection will always be a constant everywhere, as it is a direct part of entropy and the sun. And the sun is a massive entropy generator, as it causes the cycles we see throughout our dynamic, self-automated, enclosed system. What is also very interesting about these diagrams above is that it is stated in the last diagram that due to these convection cells and the claimed spin of the Earth, that air flowing north of the equator will flow right and air flowing south of the equator will flow left. But I thought the globe's atmosphere turned west to east at 15 degrees per hour and not left south of the equator and right north of the equator. This is just more global inconsistency. Temperature causes the effect of pressure in a gas as well as the phase changes of matter. But temperature is also the cause of convection, and convection is the cause of our air density and pressure gradient. And the sun causes it all, as without that there is no temperature, no pressure, and no phase change of matter. Temperature cannot exist without a heat source and gas. The pressure of gas depends solely on temperature, and temperature needs gas and a volume that is adequate enough in size to actualize. What I mean by this is, if you have a canister of gas that you can hold in your hand, it will be easy to heat it using a cigarette lighter to cause extra pressure inside the canister. But if you take that same amount of gas and place it into a container the size of a bus, then there is a lot less gas molecules per square inch, making it a whole lot more difficult to heat the gas with that same cigarette lighter. So PV equals nRT, as was mentioned above, is the basic gas law for all situations involving gas. P for pressure, V for volume of the container, N for number of gas molecules, R for the gas constant, and T for temperature. This law dictates that we must be contained as we have temperature, something that is only possible with an adequate amount of gas to heat, a heat source that is an adequate match for the container of gas that it is heating, as the gas cannot and will not stay contained in any place, coordinates, or location without a solid barrier holding it there. The gas pressure gradient cannot form in a vacuum. So, any questions on that before we go on to part 4?
This is great, very concise. Loving it so far. I've asked the chat, so there's members only chat open, and if any of the members want to ask you anything, I don't know if is that you?
Yeah, that's fine.
Is that good by you? No questions so
absolutely
far,
will.
but anybody on G Plus want to ask anything? If so, this is your opportunity again.
I'd follow with the same comment as last time. Nice summary, Brian. It's like I say, it's a lot more complicated than that, but there's nothing contradicts you. And fundamentally, yeah, the way we describe it, PV equals nRT.
Just a really, really basic question. You said PV equals nRT, B is volume. Can you have a volume without a container?
No.
Thank you.
And they're using PV equals nRT, the ideal gas law. Atmospheric scientists, as they call themselves, are using that, as was stated above. They basically contradicted themselves above when they were speaking about gas pressure and what causes it. There wasn't one mention of gravity anywhere in there. They tried to throw in the spin of the Earth and some convoluted version of the Coriolis effect, but they couldn't throw anything else in there. They tried to say without the spin of the Earth that we'd only have one convection cell, but that's not true. They have no evidence to support any of that.
I thought you got through that bit of baller rhetoric very well without choking, Brian.
Yeah.
When you reading it.
I had to read over it 2 or 3 times before I ever did it because it was hard to put it in. It was hard to not put it in there, but it was hard to get myself to be disciplined enough to just read through it because there was a lot of rubbish in there. But as I said, they debunked themselves when they spoke about PV equals nRT, the ideal gas laws. They debunked themselves with that. And they debunk themselves when they speak about density and pressure, temperature. They debunk themselves with that. So all the things that they say we need, like this spin of the Earth, and the fact that if the Earth is rotating and the atmosphere is rotating with a rotating Earth in lockstep 15 degrees an hour west to east, then how can we have all these different winds and flows of air going in all these different directions? It just wouldn't be possible.
The only thing I'd say in mitigation to that is the meteorologists will use PV equals nRT to describe a weather system, so like one big pressure of air. But that, again, isn't to negate that in full consideration, all of these little ways of describing the different pressure systems still require to be sat inside another volume for everything to work. You know what I mean? So
yeah,
they do that to create. Still, fundamentally, for those pockets, they have to sit in a fixed volume.
Brian, can you just mute while Adam's talking? Getting a lot of background noise from you.
Sorry.
No, that's it. So at the base level, they're using PVA and RT in their little systems, but what they don't use PVA and RT is in the ball model. They can't.
No, but they're agreeing here that they are using it.
Yeah.
So it's an impossibility to use it within a ball model because you don't have a volume.
Oh yeah, fundamentally, it's the only way they can describe it. Even in the, in their little models where they make a volume based on a pressure system. That's all I'm saying. That they have to use that, but they never then or can't extrapolate it out actually to their model. They can only use it within the little bits. If they then tried to extrapolate it to work it out properly, they would need the big V, the volume that all these little dynamic systems are sat within to calculate. And that's, I suppose, where they draw the Kalman line at and create an imaginary volume.
Spot on.
But that's the point. It's imaginary, isn't it? Because they don't.
Exactly. They can't get the V. That's the bottom line. Yeah, shocking. Right, Adam? They've got to use gas law. Oh, why would that be? Well, that's because that's how it behaves. But it still needs the V, and they haven't got one. That's the bottom line. I'm just going to read out a couple of comments from the chat, if that's okay with you, Brian. First and foremost, shout out to Pinpuncher, who's sharing the show far and wide and has even sent me a super chat. So thank you very much indeed, Pinpuncher. Really do appreciate your support. I'm not sure how rhetorical John M. Truth's question is, but I'll read it out anyway. Any experimentation on Earth separating gas, air, from no gas, and then he's got open brackets, high altitude, with a change of temperature, question mark.
Any experimental Could you read that again to me, Nathan?
Any experimentation on Earth separating gas or air from no gas, that could be high altitude as per their claim, I assume he means, with a change of temperature. The with a change of temperature bit threw me a bit as well, but yeah, that's his question.
Well, yeah, I think he's talking about how do you go from having gas to no gas by pure temperature alone. Basically going from gas pressure to vacuum. I think that's what he's talking about, with temperature alone. I think that's what he's talking about. But that's okay. That's going to be explained a bit later on in the... because I'm not sure if he's talking about a vacuum. Like, if he's talking about a vacuum, he's talking about, let's just say, a vacuum of space, I believe. But it's like, this is only the start. I have another 3 sections to go, and it's going to be explained. It is basically temperature is the reason why it gradiates. You know, but it all starts with the sun. Rather than trying to explain too much more now, I'd ask him to listen to the rest of it, and then if he wants to pose the same question afterwards, then fine.
Well, I think he's just qualified it a little bit further, which is to say inside a container.
Yeah, well, I'm going to be showing something towards the end here now that will show that. I don't want to say it. I'm going to tell him to watch the rest of it if he likes, and then think about his question again afterwards, if he wants to pose it again afterwards.
Okay, well, I'll invite any further comments and then one note of admin, and then we'll get back to your presentation if that's good. Any other further comments from anyone on G+? No, in that case, I'll just say in response to Pinpuncher again, yeah, feel free if you want to share this. I mean, I'd hope if you did chop it out and use it on your own channel, you'd stick a link back to this original video so people can come and subscribe to me. But yeah, feel free. Yeah, obviously, I'd hope you'd share it far and wide and smash the share buttons, which I know you do anyway. But yeah, just as a plug to that. Right, let me know when you want me to put your screen back up and you're all happy to go, Brian, and we shall do exactly that.
Okay, I'm ready to go now, Nathan.
Okay.
Yeah. Okay. 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 4, heat transfer. Some of the names of the sections I have, they're a little bit misleading slightly. Okay. Not that I don't deal with the topic. It's just the other things have to come into it. So heat transfer is a very necessary part of our system, as without adequate heat transfer, we would end up dying due to overheating of our air and earth. In our world, we have a situation where heat is created at ground level, and this heat then dissipates upward. Heat rises as the air rises once heated by the sun. Our heat source, the sun, seems to be just the correct size to match our system and has just the correct amount of heat output in accordance with us having just the correct amount of gas to heat. If our sun's output was more than it is, or we had more gas than we actually do have within the same volume container that we are in, then that would be catastrophic. The reason being that if the sun was bigger or had a more powerful output than it has, then that would cause the gas volume we have to become completely unbearable to live in, as the heat and changes in pressure, which would cause a whole lot of storms, which would make living here impossible. The sun having a bigger output would cause a lot more evaporation, so cycles like the hydrological cycle would be greatly affected, resulting in drought and flood everywhere. A stronger output by the sun would mean that the Arctic region would be decimated completely to the point where it could never return, and the Antarctica would melt so much water that the water levels all around the world would rise. On the flip side, if there was more gas than we presently have, then there would be similar problems, as there would be constant changes in weather. As there would be a crazy amount of convection to the point where we would end up with a huge amount of wind and storms, as there would be a lot more high and low pressures than we currently have. As stated earlier, if we have temperature, then we have to be enclosed, as we need gas pressure to have temperature, and we need containment to have gas pressure. And as is predicted, we need a heat source to have any of it, that source being the sun. But we also need to have heat transfer. If the heat that is created at ground level by the heating of the air, did not have adequate height above it to dissipate and transfer, this heat then would this heat would just constantly build up and up and up and up, which would be bad. So what we actually have is a perfectly sized sun that has just the correct amount of power output that heats the very adequate amount of air that we have at ground level. This heat then causes the air to reduce in density and to rise up into the sky. And in place of this warm air, we have cooler air that has raised in density while high in the sky that is coming down to replace this warm air. And the cycle starts all over again. But there is something else that is also part of this perfect system. And that is the height of the ceiling, as the ceiling is high enough to allow for adequate cooling of the Earth. A lot of people don't realize that the temperature begins to rise the closer you get to the top of the stratosphere. But at the bottom of the stratosphere, the temperature is minus 51 degrees Celsius, whereas at the top of it, it is minus 15 degrees Celsius, and even possibly more than that, as sensors from private high-altitude balloon owners have shown it to be over 0 degrees Celsius. The rising temperature near the top of the stratosphere, I will address in the next section. It is the minus 51 degrees Celsius temperature that is important here, as that would be at about 10 miles up. So that means that 10 miles up in the sky, it's already minus 51 degrees Celsius. This means that most of, if not all, the heat the Earth's surface experiences is basically dissipated or transferred to be more precise, by the time it reaches the bottom of the stratosphere, which means that the majority of the gas that has risen up due to convection will have long been cooled by the time it reaches the bottom of the stratosphere, and will have begun to have gained in density again, and will be on its way to displace the now rising warmer gases, so the whole process can start again. What is a thermal column? Up above, I was being generous, as most thermal columns don't make it past the boundary layer. So what are thermal columns, and what is the boundary layer? Thermal columns are columns of warm air that rise up in the sky due to their lower density, and then cool at higher altitudes and flow downward again, replacing the new rising newer warm air. So basically, thermal columns are columns of warm air rising up to replace the cooler downward flowing air that will replace the rising warm air. Essentially, thermal columns are a product of convection, warm-cool air replacement. Air is said to be a very poor conductor of energy, heat, in meteorological terms. So some places will have a greater chance of creating a thermal column than others. So places where the sun can warm more easily, like rock faces and man-made asphalt, are very good for creating thermal columns, whereas water is not, as the sun's heat is absorbed more by the water, which causes evaporation eventually. The water itself does not generally warm the air above it so much, or at least not to the extent that solid earth can and does. So convective thermal columns are more likely to happen over land than water, and more likely to happen where there is not too much moisture, as any water will absorb a big portion of the sun's energy. And if the water on the ground absorbs the sun's energy, then the ground gets less of this energy. So consequently, the ground won't heat the air above it as much. So in these situations, evaporation will take place first, and that is why wet solid ground will be cooler to the touch than dry solid ground. Thermal columns are used by birds and people who fly gliders to help them rise in the air up high. When thermal columns meet the boundary layer, which will be explained below, they often flatten out. So warm air is rising off of the Earth's surface, and when it meets a boundary layer, it laterally spreads out and then cools and flows down again. So you could think of a thermal column as a funnel effect. So think of a whirlwind where all the warm air rises as a big wide whirlwind, and then hits a boundary layer and spreads out, only to cool again and flow down again at the sides of the warm rising whirlwind. This would be the simplest way to describe the effect and mentally visualize it. Taking all this into account, it is very obvious that most of the Earth's air, which is 78% nitrogen and 21% oxygen and 1% carbon dioxide, argon and trace gases, never makes it past 10,000 feet elevation. This is why at the top of high mountains, there is such a lack of air, as most of the air is cycling between the Earth's surface and the sky's boundary layers. So when people are 5 miles up at the top of Mount Everest and the air pressure is only a fraction of what it is on the Earth's surface, thermal columns and boundary layers are the cause, and not a 106-year out-of-date gravity belief. The sky's boundary layer. The boundary layer of the sky, also known as the atmospheric boundary layer, is a layer of slower moving gas collisions at an average of between 8 to 10,000 feet elevation/altitude, as it is dictated by temperature. During the night time, the boundary layer gets closer to the Earth's surface as there is less heat, as there is no sunshine, obviously. The layer rises during the day as the heat being created between the sun and the Earth's surface causes the air to become less dense and rise, with the night being the inverse of this, with the air being cool and dense. The altitude of the boundary layer is determined by temperature, as air rises due to heat, but as soon as that heat is dissipated, transferred, it will cause the air to instantly slow down its collision rate and gain in density. And that is why when thermal columns meet this boundary layer, they will laterally spread outward. It's purely a situation of when the air will reach a particular temperature that determines the height of the local boundary layer. Will it reach this temperature at 2,000 feet, 8,000 feet? Who knows? Depends on the area. The elevation of the local boundary layer at any given time is dependent on temperature. The boundary layer is basically the point in the sky where different types of clouds form and a lot of dust and particles form from the surface, as well as aerosols temporarily end up. Above the boundary layer is known as the free atmosphere, as the air that does get past the boundary layer tends to be cleaner and free of dust particles and aerosols. So the boundary layer is like a filtering system of sorts, filtering the air between the surface and the upper sky. All these aerosols get dissipated there, and all the dust and other particles end up coming down either with the denser, colder air or within the rain. This means that the air that does make it through will be cleaner air, free of most of all pollutants. I'm sure this makes the airline industry happy, as this means a whole lot less rubbish that ends up in their turbines that they have to deal with. The diagram below shows the three most crucial and important parts of our density gradient: the convection cells, thermal columns, and the boundary layer, and how they work together to make sure our air is recycled and filtered clean on a daily, weekly, monthly, and yearly basis. So this here shows, first of all, the height of the warm air rising at the equator, as opposed to the height that it will rise at the let's say North Pole, and it shows the polar jet stream how it tapers downward from the equator region. It states here that the troposphere contains 75% of the mass of the Earth's surface. So that would be the tropoplane, which is that contains 75% of the Earth's atmosphere, right? The Earth's air, basically, right? Most weather occurs in the troposphere, the tropoplane, right? And there is the boundary layer. If you can see my pointer, you can see it here. Most air, majority of air that we have and gases are between the surface and the local boundary layer. So that's where most of the gases are, as opposed to above it. But it's within the tropoplane, or they call it the troposphere, is where 75% of all the air and gases are in the world. This is what's happening in simple, easy to understand terms. The sun heats the Earth's surface, causing warming of the air and then rising of this warm air. This air then, depending on where it is rising, will either meet a boundary layer or become part of the bigger convection cells, especially if it's between the tropics. The air that is slowed by the boundary layer is being cleaned and filtered, with the cleaner, less polluted air existing above it being part of the Arctic and Antarctic jet streams, which originate between the tropics. With the large volume of warm air that is rising upward between these regions being the driving force behind the Arctic and Antarctica jet streams. And these jet streams bring all this cleaner air that exists above the boundary layers towards the Arctic regions and back along the Earth's surface once more. All of this starts with the sun, as without the sun, there would be no convection cells, no thermal columns, no boundary layers, or air pressure or evaporation, or air pressure gradient, or to even argue over. So without the sun, we wouldn't even have an argument because it wouldn't be happening. It all starts and ends with the sun. 75% of all our air and gases are within the tropoplane, formerly known as the troposphere. So from surface to 10 miles up in the sky, 3/4 of our atmosphere exists, with the last 25% existing in the stratus plane. Something that will be triggering for a lot of people to hear and believe. Okay, that's the end of 4th part. Anyone got any questions?
Feel free, G+ panel. I've got one question.
Yeah.
Well, you kept saying barrier layer, and I don't know if that's just a terminology thing in terms of your arbitrary position where the 75% and 25% distinguish themselves. That bit I didn't quite follow.
Well, it's what I was saying was boundary. Maybe it's my accent. Boundary, boundry. They call it a boundary layer. It's basically the best way to describe what a boundary layer is if you know in a warm day the clouds will be higher in the sky than on a colder day, or higher in the sky in the daytime than in the nighttime. It's because of temperature. The more warm air rises, the higher the boundary layer is. The boundary layer is just basically a change. It's basically just where a change in temperature that basically holds on to a huge amount of the air and water vapor and all that. And the boundary layer is basically where clouds and that start to form. And that, you know, it's kind of the average area where clouds start to form.
I just don't know the terminology. Boundary it sort of infers that there's a boundary, whereas in reality it's just that temperature, wherever the height of that temperature point is where that phase change starts to occur, will be where that layer occurs. But there is no boundary. But yeah, okay, fine.
Yeah, it's their terminology. And a better way to describe it would be a temperature boundary, maybe, or something like that, because it's purely temperature related. But they call it a boundary layer.
It should be called a transition layer because there's transitioning happening, and it can shift, you know, depending on what's piling up. It could be migrated. Sometimes the clouds are really high up, sometimes they're not so high up. So it does shift around. It's not really a separated layer.
Yeah, no, I agree. Their terminology is very, I suppose it's for descriptive purposes. They're trying to show people that this layer, they call it a boundary layer, stops at a certain point and it stops things going through, but it can't because it's gas. And a lot of the air does go through up above that and becomes part of the larger convection cells. But it's basically a filtering layer, if you want to call it like that as well, because it filters out a lot of the rubbish. So we end up getting basically cleaner air. We end up getting our air cleaned by these boundary, what they call boundary layers. And this air then is recycled back to us due to the larger convection cells. But what did you call it, Arwen? That was a good terminology.
A transition layer. It's not a boundary.
Transition layer. Yeah,
it's a transition. So it could be compared to the supersaline layer at the bottom of the ocean at some points. It keeps itself separated, but technically it's only separated. It's arbitrary. Its position in relation to the other layer is pretty arbitrary because if there more of that same substance would pile in there with the mesh, then it would all move, right? It would move up or move away. But yeah, there is a separated transition layer, but its location is basically dependent on the material and the conditions present.
Transition bit I like, but the layer bit I don't. So, you know, we're talking about an anisotropic, inhomogeneous mixture of gases and then describing them as layers or boundaries. And it's like, okay, transition, yeah, that's good. Well, it's the phase transition. Well, the height of the phase transition would be the where of this particular description, whereas they've got it described with a boundary and with a layer. Well, that's all very useful for heliocentric rhetoric where they've got air spheres and tropospheres and various other things with layers between them. Whereas in reality, it's like, well, no, it's like the horizon. It's massively variable. Depends on the weather. Depends how hot it is that day. Depends on what's already formed beneath the two layers in terms of the phase change of the water, for instance. And that may change the temperatures below, therefore changing the effect again. So there's a huge amount that goes into it. But there is no layer. There is no boundary.
Well, still, though, a boundary really emphasizes the separation, while a layer, a layer of fat is going to lie on water, but it's pretty arbitrary. It's just that is where it kind of tends to separate, but the location is pretty arbitrary.
Exactly. Yeah. Anybody else got anything to add before Brian moves on with this?
Yeah, I was gonna say, wouldn't it be easier to call it an interaction?
It's a location, though, isn't it? So you're trying to describe a location as a phase change transition, and it's like, well, that's not a location. So it's the phase change transitional height, maybe.
It's a bit like the horizon. It moves with the weather. It's a point that moves with the weather. If you see it described like the horizon, it moves with the weather. The warmer the weather, the higher the local your boundary there will be. So if I'm in a colder temperature-wise place, yeah, my boundary layer will be closer to the surface. They call it boundary layer. Will be closer.
I'll be honest. I have noticed that, man. It's funny because I made that observation like a few weeks ago. I was like, the clouds look so low, and it seems like when it's cold and shitty out, that's when it seems a real low. But then when it's hot, warm, it's beautiful, they seem really high. So that's an interesting point.
A couple of quick shout-outs. So another shout-out to John M. Truth, who's the only one interacting with the discussion, which he says, boundary is kind of pressure transition opposition. Again, we're all kind of coming up with these terms when we're trying to describe a location in the sky that's got a rubber ruler attached to it. Also, a shout out to Retrobit, who says, thanks for the great show. Well, that's down to Brian, so thank you very much to Brian, and thank you for the super chat.
Well, within the container, so we have air pressure. I think what Brian's doing, and I'm following, I love this presentation, where the sun transverses the earth, if I'm saying it right, in those areas is where all the heat is generated. And then towards the edges of this plane, where the Arctics are, it reminds me of that map that Paul showed that he has to go to the Wayback Machine of the weather patterns. And when you do it on the circle, remember that?
Yes.
This is the image I'm getting as you're talking,
Yeah.
because all the currents come back down towards the edges.
It's a random.
If boundary or layer are objectionable, then maybe just call it a zone. No?
Yeah, that's not bad.
Transition zone.
That's good, actually. Phase transition zone.
Yeah, because that's what's happening. Basically, it's the water vapor. Is basically what's happening is the water vapor is changing phase at that height. So when basically on a warm day, the water vapor is less likely to change into a cloud close to the surface because of the heat making it all rise. And on a warmer day, it's more likely that the H2O molecule will go through a photodissociation where it's broken apart, as I say. But whatever condensing of the water vapor that happens will happen up higher because it was more warm air. Basically, so it's whatever layer due to the temperature of the day that water vapor condenses into a cloud. And the cloud basically traps. It's the water vapor that traps a lot of the pollutants and the dust and all that kind of stuff. So that's a big part of it. So that's why often it can rain on you. And you end up, if you dry, you have little bits. You'll actually have little bits of dust and stuff on you because it's coming back down from being trapped by that. So the clouds basically and the water vapor create a kind of a filtering, whereas the oxygen and the other gases. Some of the other gases can keep rising, but can keep going past that point. But the water vapor obviously has the phase change due to the temperature faster than anything. So
Right. So the clouds, the condensed air part, basically functions like a scrubber, scrubbing all particulates and solids and dust out of it, and then helping it back down through rain.
Now, obviously, there's different types of clouds, and they form for different reasons. Obviously, temperature is the main part behind it. So this is not a kind of it's just a kind of a basic description. But obviously, people could say, well, there's this type of cloud that forms at this height, and that type of cloud that forms at that height. Yeah, okay, that's all fine, and I don't mind that argument at all. But as a basic description, the boundary layer is where basically a lot of these things are stopped, and they're stopped by basically the transition phase of the water vapor, basically.
Okie doke. Anybody else got any more? And then if not, we'll move on. No? Brian, is this your last section?
This is the second last, but the last section is just kind of a tying up, but this is the second last section. Okay, I just want to fix up the water, and I'll just, because my metal's a bit dry, and we'll get going. So this is called low-grade vacuum. There's some stuff in this I can't expect everyone to go along with in this section, and I understand that people don't, but I'm putting it out there as my claim and not anyone else's claim.
Okay, ready when you are. Everyone else, if you can put yourselves on mute.
So low-grade vacuum. So, thank you, Nathan. Most of our atmosphere is made up of two main gases, nitrogen at 78% and oxygen at 21%. And these both constantly cycle with the Earth in a never-ending type of reoccurring Groundhog Day. The nitrogen cycle has 5 steps. 1, fixation, is where nitrogen gas is transformed into a different state, a state that plant roots can take advantage of and use. 2, mineralization, is where nitrogen is further converted from manure, decomposing plants and animal material by microbes into a food for plant life. 3 is nitrification, is where the ammonia in the soils that was produced due to mineralization is turned into nitrites and nitrates. Nitrates can be used by plants and animals, but nitrites cannot. So 2 types of bacteria called Nitrosomonas and Nitrobacter help disband this divide. Nitrosomonas transforms ammonia into nitrites, and Nitrobacter transforms nitrites into nitrates. These bacteria are also energized through this process, a process which can only happen in the presence of oxygen. The process is very important as it gives plant life an extra stash of needed food for energy. 4, immobilization is described as the reverse of mineralization, as microorganisms in the soil pull nitrogen from the soil when there is not enough in the decomposing plant life, which ties up the amount of nitrogen in the soil that is available to plant life. This process is very important as it keeps the amount of nitrogen being used in the form of nitrates by plants in balance. 5 is denitrification, is where nitrates are turned back into nitrogen gas by bacteria in the soil, returning the nitrogen back to its original starting point to continue being 78% of our air supply. The oxygen cycle. Oxygen is produced for us to breathe in 2 ways, photosynthesis and photodissociation. Photosynthesis is where plant life and sea life like phytoplankton and seaweed use carbon dioxide as part of their energy source, converting and releasing this eventually as oxygen into the air. Photodissociation is where the H2O molecule is broken apart by sunlight, releasing the singular oxygen atoms into the air, where they eventually pair up with other oxygen atoms, creating O2 and supposedly O3 ozone. Humans and animals then use this O2 through their inhalation of air and exhale carbon dioxide afterwards, which is then used by plants and sea life. And the process starts all over again. Most of the Earth's oxygen is not in gaseous form and is found inside the Earth, and especially in our oceans, rivers, lakes, and ice. So 78% of our air is nitrogen and 21% of our air is oxygen. 78 plus 21 equals 99. So 99% of our air is constantly used and recycled at and with ground level, as it has to be for the continuation of life here in our world. So if 99% of our total air supply is constantly used within cycles that are absolutely necessary for the total health of our system, where these gases take on other forms in several different ways to feed the system's organic matter and then return to gaseous form for us and the animal life to breed, then is it any wonder we have a gas pressure gradient? As we can't not have a pressure gradient under those conditions where it is absolutely necessary for 99% of our air supply to constantly recycle itself with the solid earth underneath. Remember, these cycles are only possible due to us having a sun, as without that there is no cycles. These cycles go under the umbrella of the biogeochemical cycle, which includes not just nitrogen and oxygen, but also water, carbon, sulfur, and phosphorus. All these elements are recycled with the earth all the time. Some questions I could not get answered, regardless of what way I asked them, or what way I formed the questions to Google. 1. What process brings the oxygen and hydrogen atoms back together that were split apart by photodissociation? And 2, what happens to all the hydrogen that is split apart from the H2O molecule by photodissociation? Where does that go? Basically, I'm asking what reforms the water molecules that was taken apart by the process of photodissociation. How and where does it reform? What exactly is water, and what originally forms it? And what is all the hydrogen that is separated from the oxygen atom by the sun used for? These are very interesting questions, things I can't get answers for. Now, if people looking to see what these are and try to find answers for them, a lot of the ballers, or sorry, the opposition, will say they'll think they already have the answer to this, and they'll just give me photodissociation again, right? Which is not the answer. The point is what happens after photodissociation. How does water reform, and what happens to all the hydrogen that is taken from the H2O molecule by photodissociation? We know what we're told the oxygen does. We're not told about the hydrogen. What does the hydrogen do? Where does that go? What is that used for? Because it has to be used for something, because the earth doesn't form things for no reason. It didn't just disappear. It doesn't just disappear. It doesn't just wait for oxygen to come back to it. So if you're on the opposition side and you're trying to answer this question, remember, think about what you're asking, because there's no point coming back to photodissociation again. That's pointless. You see, I have a lot of questions about our world, and in my investigations, I've found some inconsistencies. And one of those inconsistencies is the ozone layer. The ozone layer is claimed to be between 9 and 18, and 7 and 25, and 8 and 22 miles up in the stratosphere. It is claimed to protect us from harmful sun rays, and is the reason why the temperature in the stratosphere rises as you rise through it. The stratosphere holds the last 25% of our atmosphere, with 21% of that last 25% being O2, and the rest being mostly nitrogen and trace gases. So I don't mean that there's 21% of 25%. I'm saying there's 25% of gas left in the stratosphere, and if that, you have to make that 25% into 100%, and 21% of that 100% will be oxygen, and 78% will be nitrogen, and the rest, the 1%, will be trace gases. But 21% of that last 25% will be O2. The temperature at the bottom of the stratosphere is minus 51 degrees Celsius, which is 10 miles up. And this region stretches another 20 or so miles up. So whatever air is getting past these minus 51 degrees Celsius temperatures has twice the distance vertically that the other 75% of the air had to stretch, with most of the 25% in the stratosphere towards the bottom. So that's not a whole lot of O2 to go around. And if only some of this is becoming O3 ozone, then with only 21% of the remaining 25% of air being oxygen, O2 molecules, and only some of this remaining O2 becoming O3, then how is this creating such a temperature rise? If the O3 molecule is created starting with photodissociation of either O2 or H2O molecules, then that's an even bigger problem. At minus 51 degrees, there was no water molecules getting past that temperature, as they would have long become ice. That is why Antarctica is considered to be a desert, as it is so cold that there is no water vapor in the air, so no moisture in the air. So this means that there can only be O2 molecules being broken apart by sunlight to join up with the other O2 molecules to form O3, ozone. But either way, it doesn't matter, as the pressure gradient shows that we have less and less air as we rise. Taking this into account, it means that between 10 miles up and 30 miles up, there is less and less air, and only 21% of this air is oxygen, and how much of this oxygen becomes O3, ozone. The total amount of ozone in the atmosphere is 0.00006%, and the concentration of O3 ozone at 20 miles up is claimed by NASA to be 0.0015%. This doesn't seem like anywhere near enough ozone to me to bring temperatures from minus 51 to minus 15 degrees Celsius, and maybe even more, maybe as high as 0 degrees Celsius or even further. This whole claim is not making any sense, especially when we take in the fact that the air is less and less and less in amounts from 10 to 30 miles up. With high-altitude balloons have shown that the air pressure gets as low as 10 to the minus 2 torr, 3/4 of the way up the stratosphere. Yet the temperature continues to rise even though there is hardly any gas to insulate us from the sun. And how much of that gas is actually ozone? This means that the claim that the ozone layer, if it's there, is insulating us from UV rays, creating a heat blockage, is and must be false. I predict, this is my prediction, not for the panel, my prediction personally. I predict that the heat we are encountering is coming from the top down, as something is being heated above us by the sun, but not just the sun, as this surface is also acting as the insulator the ozone layer is claimed to be, but obviously cannot be. And I believe this surface to be the ceiling of our system and world. And to add credence to this claim, I would point out that there is no measurements, readings, or proof of anything past 30 plus miles up, as that is the maximum height of a high-altitude balloon. All high-altitude balloons break apart around this altitude. You see, past this 30 plus miles point, all claimed and supposed measurements of pressure and temperature are taken from space agency sounding rockets, which are claimed to travel to a sky vacuum and return a type of data pod that was supposedly originally placed inside a rocket. But we know this can't be real. So what then is creating our evacuated top? As the official story does not fit with reality, as there is no accounting for the rise in temperatures or how it is possible to have a gas pressure gradient form in a vacuum. That simply does not happen. Okay, that's the end of part 5. Any questions before I do the last section?
I think it's a little confusing to kind of like at one point address the spherical layout of the sphere and all that in the ozone layer, and then get back to the real world when it's already really complicated in the real world. So getting a little confused here and there.
Well, I'll clear up the ozone part. It's claimed that the reason that we have rising temperatures from the bottom to the top of this, what they call the stratosphere, is because of the ozone layer, right? The ozone layer creating an insulation, right? But as I showed, at 20 miles up, according to NASA, the concentration at 20 miles up, this is not even 30 plus miles up, at 20 miles up, the concentration of ozone is only 0.0015%. It is nowhere, and there is less and less and less gas as you rise. So that means there is less and less and less O2, and that means there is only a tiny amount of ozone if they're talking about, because there is no water molecules getting past minus 51 degrees at the bottom of the stratosphere. Right, I'm going to use the general term. I'm going to say stratosphere for this. At the bottom of the stratosphere is minus 51, so there's no H2O getting past that point. So you only have O2 to make O3 from. So consequently, and there's only a small amount of that O2 is turned into O3. So at 20 miles up, if there is only 0.0015% O3, that means that 30 miles up and 30 plus miles up, which you could be talking up to 36 miles, right? There's hardly anything. So how come there is a rising in temperatures? Another surface has to be heated above us. And there's hardly any gas. The less and less and less it rises, but yet there's still a rising in temperature. That means there is another surface. Because the sun, right, it heats the surface of the ground, which heats the gas that's above the surface. But obviously, there's something similar happening above us, because it can't be ozone.
You mean what they call the troposphere, right?
Well, I don't.
They call it the troposphere. Is that heat part?
Well, there's not. Basically, I'm claiming there's nothing much past the stratosphere. Nothing past that doesn't exist.
All right. But I don't really understand why there has to be a layer up there actually causing heat again.
Well, yeah, that makes no sense.
The surface is what I'm saying. It's the ceiling. That's the ceiling. The surface of the ceiling.
Why would that be hot in any form? It's just the ceiling, right?
Yeah, but the sun would be heating the ceiling.
Oh, yeah, but now you're actually threading on my original objection that I did not speak out the entire presentation. So
we might get to that at the end or discuss it in the after show. But is there any other questions on part 5 before we move on to part 6 from G+? And then again, John M. Truth has got something to add. You might be able to comment on that as well. Anybody in G+ first? Adam, go.
Well, if I may. Oh, Adam, want to go first?
We've already heard from you.
Just a point of clarity, so just be quick. Brian was talking about the upper bit being only 25% of the total molecules, and then describe just to clarify, because I got a bit confused. Are you saying there's less of it, but it's the same composition?
Yeah, the composition is not changed. The difference is after the bottom of the bottom of the stratosphere, which would be the top of the troposphere, right, which is 10 miles up. That's minus 51 degrees. So there's no water vapor getting past that without turning into ice. So there's how much water vapor? The reason I'm saying that is O3 ozone, right, is made from either the breaking apart of the H2O molecule or the O2 molecule, right? So it's either oxygen or water breaks that apart that creates the O3, the ozone. But the problem is they only have O2 past 10 miles up. They only have O2, and there's less and less and less of that for the 20 plus miles it goes up to the top of the stratosphere. So consequently, they only have whatever bit of O2 is there to work off. And at 20 miles up, the concentration of O3, according to NASA, is 0.0015%. So it would be even just a tiny fraction of that 25 miles up. So they're claiming that they have this blanket of ozone creating this insulation, which causes a heat rise within what they call the stratosphere, right, the stratusplane, right. It has to be completely rubbish because it isn't enough.
But do they actually claim that though?
Yes, that is
I thought the ozone layer only was supposedly protecting us against certain types of solar radiation, not actually keep the heat in.
No, they claim it. They actually claim it's creating insulation, and it's that insulation that gives us the rising temperatures.
Yeah, greenhouse effect. So
yeah.
But I thought that was basically just sunlight reflecting. It's so convoluted by now. It's all spherical-based ideas anyway. So
I know.
But how does ozone get up there? I don't know. Look, there's ways to make ozone. Electrically, and with light potentially. So it could be that even the relatively thin gas is not the water, which is not going to reach it, because of the temperature, it's going to get liquid and then fall down again due to relative density. But I think that other influences might actually kind of rearrange the gases up there into ozone for a certain percentage. I think that might be possible.
Well,
I think
I'm
that's
not
right.
saying.
Brian, is that not your point, that there's not enough of this stuff to even form, excuse the phraseology, a layer? That
Yeah.
whatever there is, and the point of ozone is it's supposed to reflect UV away and stop
Right.
the level of penetration, whereas CO2 is supposed to contain the UV. But what you're saying then is that there's not, so even if you, because of the composition being only being 20 odd percent be up there, even if you forgive that there might be a little bit more percentage rise because there's no water, there's still nowhere near enough ozone per se to form a layer, never mind the pretense that gases are going to form a layer based on.
Well, yeah, if you look at what
It's
NASA
an
says,
exaggeration.
and NASA says even at 20 miles up, there is only 0.0015% of the concentration of air up there is ozone. And that's at 20 miles up. So the further you rise, that means that number is getting smaller. So that tiny amount of ozone will be nowhere near enough to cover what would be basically to be so, there was so little ozone. I'm not saying there isn't ozone, it's just there was so little ozone that it could nowhere near be enough to create an insulation, which they claim is the reason for our rising temperatures from the bottom of the stratus plane to the top. So we have a rising temperature they can't explain, and they try and use ozone to do it, but there's nowhere near the amount of ozone they need.
Right. So we could conclude out of this data analysis and what's actually there, that the entire foundation for any kind of climate change influence is completely bunk and about as reliable as the seismic, or what is it, the geological predictions of what they would find in the deep borehole, basically.
Yes.
All right, I agree to that.
Yeah.
Okay, can I just seek out an answer to a question that I think is seeking clarity from part of your presentation again from John M. Truth? I might have to paraphrase it slightly. So is the official amateur measure, not NASA measure, colder temperature minus 51 Celsius? ? That's from John M. Truth.
Yeah. The temperature at the bottom, from amateurs, the temperature, if you look at even the Mage balloons, the temperature at the bottom of the stratosphere was pretty much in accordance with what was the official. But as it rose, the Mage, I don't know about the first Mage balloon, but the second one that was done, that showed. I know you're working off of his the Mr. Sensibles, because he's the guy who did the most recent ones. I'm not working off the other flat out ones. His rose to a temperature of, when it got to 30, what was it? Was it 47 kilometers up, which would be close on 26 miles or something like that. It rose to plus 4 degrees or something like that. So there is a massive rise in temperature from the bottom of what they call the stratosphere to the top. They try and say officially it's minus 15, but his sensor showed it to be way more. And now I would say it's very likely that other people might have got similar, like Dwayne Kellum, who did a lot of high altitude balloon stuff. He might have got very similar readings, I don't know. But I know that there is a temperature rise. That even if they take the official one from weather.gov, it's minus 51 to minus 15. That's a huge rise in temperatures, considering that there is so little gas. Something has to be heating. Something has to be causing this heat. And what would cause a heat would be another surface that's being heated. And this heat is somehow permeating through whatever gas is, whatever a small amount of gas is up there, permeating through that gas, even though the gas is getting less and less and less. So if the gas wasn't so little up there, the heat would, I predict the heat would be phenomenal up there. But there is the main people should take away from this, regardless of whether they believe that that's a ceiling, like I'm basically saying it's our ceiling that's being heated, and that's causing the heat. That's causing, and also when it's causing an insulation for wherever heat has risen. But people have to take on board, even if they don't want to take any of that in and they don't believe any of that or they don't accept it, they have to take on board that past the stratosphere, the top of the stratus plane, the stratosphere, if you want to call it that, there is no evidence of any measurements of or readings of anything, because after that, there is nowhere for high altitude balloons to go, because high altitude balloons can't make it past that point. So every reading and measurement after that comes from NASA and space agency sounding rockets, which are claimed to go off out into a sky vacuum, an entropy violation, and then bring back a pod with all this data on it. So that has to be false, because we know that's not real. So there is no evidence or measurements of anything past the top of the stratus plane, stratosphere, whatever you want to call it.
Okay, I can't see any other further questions from chat unless there's anything else from G+. We'll move on with the sixth and final section. Go on, Owen.
I'm just thinking in my head, like, really, there's a temperature rise, and Brian basically thinks it's because there's a barrier there that is somehow being heated, at least at regular intervals, I take it, not constantly heated. But where's the evidence? If there was sunlight basically heating it up, well, then there would have to be sunlight visible, like at that location. Like, heat gives off heat signature. You can see heat with a heat seeker. Where is it?
Well,
where's the heated surface? Here on Earth, when something is heated, you can look at it with infrared vision and you can see it's heated. So where is it heated up there?
Okay, go ahead, Brian.
Well, the temperature is rising. That's the thing about it. There is like, you can measure the temperature rising as you go through the stratus plane or stratosphere, whatever you want to call it. The temperature continues to rise. And as I said earlier, it gets to a certain point where you can't take any more measurements, because high altitude balloons won't get past that point. Won't get past about 30 miles up. Around 30 miles up, it won't get past. And I'm predicting that the ceiling is a couple of miles past that area. What I will say is, when any balloons get up there, you can see it's never nighttime up there. It's always bright. You can always see up there. There's no nighttime up there, if you understand what I mean. You can always see. There's no night. You never see it. Like, there's no nighttime high up at the top of the stratus plane.
I disagree. I think you definitely always see the daylight beneath, but up there it's always dark. So you can't really define it as day and night anymore.
Yeah, well, it's not dark.
Stars.
You can always see. I never see a high altitude balloon that can't see up there. But that's kind of the point I'm making is, the only thing we have to go on past a certain point is NASA rockets out into a sky vacuum. And the thing about it is, we know we're enclosed, so the ceiling has to be there. Whatever the ceiling is, I don't know. Whatever shape it is, I don't know. But it has to be there, and it has to be able to contain us. And I don't see why the sun could not be having an adverse heat effect on a separate surface, just like it has on the surface here of the ground. If we have heat on the ground, then why can't we have heat on the ceiling?
I understand the concern, but I'll keep it short, okay? But look, here on the surface, we can see the daylight being absorbed. We can measure it. We can see it with infrared. Up there, there's no such thing. And I don't know if anyone has done that. I really don't know. I'm only going off of what they should. Am I causing feedback?
Yeah.
Right. I wanted to tell you that I totally agree about there having to be a ceiling, though. But the temperature, sunlight hitting it, that's where things get a little complicated. I don't think there's any kind of light manifest up there that goes through a barrier or goes upwards in any way. But yeah, it's not fully researched yet, so it's worth investigating.
Yeah, okay, that's fine. That's fine. It's my claim personally, so it's not on anyone else. Okay, and I don't mind being wrong about it, but I accept that claim, and I understand Aaron's questions. I do. So I'll get to, yeah. Okay, the last section is just going to be 22 facts, final words. Okay, so the low-level vacuum is created by the sun. This is my claim, that the lower-level vacuum, the 10 to the -2, 10 to the -3, whatever it is up there, is created by the sun. Okay, number one, the sun is the cause of all the convection that takes place here on Earth. Number two, the sun is the driving force behind the nitrogen and oxygen cycles, as without the sun, they would not exist. Number three, the sun is the cause of all temperature changes both on the surface of Earth and in our air and sky. Number four, the sun heats the surface of the Earth, which then heats the air. Number five, the sun heats the air to heat and rise through this process. Number six, the sun causes temperature, and temperature determines gas pressure and gas density. Number seven, the gas causes the sky's boundary layer. Number seven, the sun causes the sky's boundary layer, which holds most of our air within it and changes in altitude from night to day. 8, above the boundary layer, which is caused by the sun above the boundary layer, which is caused by the sun, temperature, gas pressure, and gas amounts stay relatively constant. 9, below the boundary layer, which is caused by the sun, remember, temperature and gas pressures change constantly from night to day and season to season with weather. And so above the boundary layer, temperature and pressure stay more constant, but below the boundary layer, both temperature and pressure are more changeable. And don't forget, the boundary layer is a product of the sun. 11, there is more air below the boundary layer than there is above it, all caused by the sun. 12, nitrogen and oxygen make up 99% of our air supply and constantly recycle with the solid Earth. Cycles only possible due to the sun. 13, there is a much greater amount of warm air rising off of the Earth and rising higher than any other warm air does anywhere else on the Earth between the tropics of Cancer and Capricorn due to the sun. 14, this higher rising warm air caused by convection, which is a product of the sun, then flows eventually towards the Arctic regions and back along the Earth as a type of filtration system for our air in accordance with the Earth's boundary layers. 15, the filtration system caused by and dependent on the sun keeps our air clean. 16, if the sun is causing a temperature gradient from the Earth's surface up into the sky, then the sun is also causing an air pressure gradient from the ground up into the sky. 17, if the sun warms the air through heating the Earth's surface and 99% of the Earth's air is constantly recycled with the Earth's surface, that would mean that we would have a temperature and air pressure gradient that starts at the Earth's surface and gradiates upward, lessening in temperature and air pressure as you rise. We do have that, so that means that it is caused by the sun. 18, due to the nitrogen and oxygen gas cycles, convection cells, boundary layers, thermal columns, Arctic and Antarctic jet streams, temperature, air pressure gradients, and the rest of the biogeochemical cycles, including the hydrological cycle, all caused by the sun, remember, we can't not have a dynamic gradiated system. So it's impossible to not have that with all those things. 19, as a matter of fact, our system gradiates so much due to the sun, remember, that we end up with a low-grade vacuum just under the roof of our structure. 20, and how do we know that this low-grade vacuum that is caused by the sun is just under the ceiling of our Earth structure? 21, because only 21% of the small amount of air that is at the top of the stratus plane is oxygen, and only a small amount of this O2 turns into ozone O3, with the concentration of ozone being 0.0015% at those altitudes, which is not enough to cause an insulation of heat, yet we do have rising temperatures from the base to the top of the stratus plane. So the only way to cause these rising temperatures is by the sun heating a surface. 22. And this surface is the ceiling, the roof, the top, whatever it is, whatever it's made of. It allows for radiative heating due to insulation caused by the sun. And if there wasn't so little air up at these altitudes, the heat would even be more than it is. If there wasn't so little air up at these altitudes, the heat would even be more than it is, as the air is decreasing in amounts and by proxy pressures due to the gradient caused by the sun, while the heat is increasing the closer to the ceiling we come. Think of a huge thermometer or barometer with an internal heat source that causes dynamic cycles. Heat causes the mercury to rise, and cold causes the mercury to fall. But all the while there is a vacuum above. You see, the sun is the reason we have a pressure gradient, and the pressure gradient creates the vacuum due to the sun. And as we all know only too well, a gas pressure gradient will not form inside a vacuum. But a gas pressure gradient will create a vacuum, but to have a gas pressure gradient or a vacuum, you must have containment. And to have a flat, stationary, enclosed, self-automated dynamic system with an internal gas pressure gradient and vacuum overhead, then you must have a sun, as the sun is the antecedent to the formation of a pressure gradient and vacuum, with the exception of a container and creator. The end. That's it.
What a lovely day!